All right, so in the next portion of today's lecture, we're going to go over some basic course overview and some course policies. So welcome to CSW 182 or 282A, Designing, Visualizing, and Understanding Deep Neural Networks, or as we could call it, the Deep Learning class. So a brief overview of what we're going to talk about in this course. We will talk about GANs, we will talk about how to generate faces, how to turn tigers into cats, and how to get a robotic dog to walk. We're going to have a broad overview of deep learning topics. So this course is really meant to give you kind of the lay of the land in the world of deep learning. We're going to talk about neural network architectures. We're going to talk about optimization algorithms. We're going to talk about some applications. We'll cover applications in computer vision, in natural language processing, and probably a few other areas. We will discuss reinforcement learning. We'll discuss how you can use deep neural nets to learn behaviors. And we'll cover some advanced topics. Still TBD as to what exactly those topics will be. Maybe we'll have some discussion of transfer learning or meta learning or other cool things like that. There will be 4 homework assignments, and they will be programming assignments. So these assignments will require you to write some code and make sure that code actually works. So you will implement some neural network basics. You'll actually code up some convnets and some neural networks and backpropagation and things like that. We'll have a homework assignment on convolutional networks and recurrent neural networks. So most likely that assignment will involve implementing some kind of like image captioning system that has to read in images and maybe produce text. We'll have an assignment on natural language processing, and then we'll have an assignment on reinforcement learning. There will be 2 midterm exams in the course. The particular format is TBD. Right now, we're thinking that we'll probably make them take-home exams, but that remains to be decided. So we'll have 2 midterms. And then we'll have a final project. And the final project is very important. It'll be a large portion of your grade. It's a group project, and we recommend groups of 2 to 3 people. It's one of the most important parts of the course in terms of your homework. There will be slightly different rules for final projects. If you're in CS 182, the undergraduate version of the course, you can choose from among 3 topics: computer vision, NLP, or reinforcement learning, and we'll have some materials for you to get you started. If you are in the graduate version in 282A, the final project is a bit more self-directed and open-ended, so there you would write a proposal for kind of a research-focused final project. And we will release the instructions for that probably in a few weeks. Course policies. So your grade in this course will consist about 30% of midterms, so each midterm will be 15% of your final grade. 40% for your programming homeworks, so each of the homeworks is 10% of the grade, and then 30% will depend on the final project. So the final project is a large portion of your grade. It's as much as both midterms combined, so you definitely want to make sure that you get started on your final project early. In fact, you should feel free to start talking to some of your peers, to form groups, even right now. Some logistics things, late policy. Don't be late. You should complete your assignments on time. If, however, you do not complete your assignment on time, you have 5 slip days. The slip days are always rounded up to the nearest day. So if your assignment is, an hour late, that is 1 slip day. If you use more than 5 over the course of the semester and then you turn something in that is late, then you will get a 0 on it. So definitely don't exceed those slip days. I don't recommend using the slip days unless you really, really have to. Like, save them for when something really goes wrong, when you have an emergency, when you really need them. Don't use them up early. Definitely don't use them up on the first homework assignment. So we have a strict late policy. There's absolutely no slack beyond the slip days, so do make sure to stick to that. And for the final project, there are no slip days due to the grading deadlines, so you want to turn in your final project on time. Prerequisites for the course. You should have an excellent knowledge of calculus and linear algebra. This is very, very important. So a lot of material in deep learning draws very heavily on linear algebra, and you want to have good familiarity with multivariate calculus because a lot of the optimization algorithms that we use in deep learning make use of multivariate derivatives. So you should especially be really solid when it comes to multivariate derivatives. So how do you take the derivative of a matrix vector expression with respect to a vector? You should be really solid on matrix operations and on solving linear systems. If you're not sure about this, maybe pay attention in the second and third lectures when we'll talk about basics of machine learning and basics of backpropagation and gradient descent. And if things there are looking really tough from a math standpoint, then maybe reevaluate whether you really meet the prerequisites. If you're not sure about this, feel free to come to talk to me or to the TAs. You should have excellent knowledge of probability theory, CS70 or STAT 134. CS70 just kind of barely covers the probability that you need. You can probably make it through with CS70, but be prepared that it'll be a little harder going, that you might need to brush up on the probability theory a little bit. Definitely you should know how to deal with continuous random variables, Gaussian or normal distributions, multivariate normal distributions, things like that. We recommend CS189 or a very strong statistics background. So we will cover a lot of machine learning basics in this course, but we'll cover them very, very quickly. So we'll essentially cover what CS189 covers, but in like one lecture. So strongly recommend that you have taken CS189 or have a very strong background in probability theory and statistics. You'll probably get an idea for for the pace of things in lecture 2 and 3 in regard to that. So if in lecture 2 and 3 you feel pretty lost and you haven't taken CS189, maybe it would be a good idea to take CS189 prior to taking this course. And of course we require you to be able to program, so we want you to have taken CS61B or something equivalent and to be able to write fluent code in Python. And again, if you're not sure about something here, a really good way to quickly get a sense for whether you've got the prereqs is to start on homework 1 once it's released, which will be most likely 2 weeks from now. Start on it early and just see if it's tough going or if it's going pretty well. Okay, so in the next portion of the lecture, we'll cover the following questions. What is machine learning and what is deep learning? So many of you probably have some idea of what the answer to this question is, but you can think of a very basic machine learning problem as something like this. You've got a picture, maybe you've got a picture of this puppy, and you want to write some kind of computer program that produces an object label that takes in a picture and tells you, does it have a puppy or not? Or does it have a puppy or a cat or an elephant? So you could go and try to code up this computer program. You could, write some if statements and some code and things like that to kind of program in your best attempt at a puppy classifier. But how would you implement this program? Well, this would be pretty hard. Like you could say, well, you have some knowledge about puppies, like they have 2 ears, 2 eyes, and a nose, and a tongue, right? But what's an ear, and what's an eye, and what's a nose, and how do you detect it from pixels in an image? A lot of early work in computer vision actually tried to take this approach. It tried to describe how images work, how they come about due to geometry in the world, the effects of lighting, and so on, actually program in some code that would attempt to invert that process. That approach turned out to not work very well for computer vision, but it did work really great in computer graphics. So while a lot of early work in computer vision and computer graphics had a lot in common, most of that work ended up culminating in the computer graphics systems that you see today when you watch movies or play video games. Hasn't really showed up in a lot of the work on computer vision when it comes to actually recognizing puppies in photographs. So maybe we'd like a better way to create this program. Maybe we don't want to write it by hand. You can think of a function, and that's what a program is. A program is a function, as a set of rules for transforming inputs into outputs. That's kind of an obvious statement, right? Functions turn inputs into outputs, programs are functions, therefore programs turn inputs into outputs using some rules. And sometimes we can define these rules by hand. And that's essentially what programming is. When you write a program, you're defining rules for transforming inputs into outputs. The trouble is, with problems like this, problems like recognizing this puppy, the rules that govern the transformation from inputs to outputs are quite complex, and they have a huge number of exceptions. They're perhaps not so complex algorithmically. It's not as complicated as writing code that will perform like a graph search or something. But that's actually what makes them so hard to program. See, we're pretty good at writing simple rules that create kind of a deep stack. recursive algorithms, things like that. Those are great because the code is really short, but the program does something really complicated. For recognizing the puppy, it's kind of the opposite. The program is probably pretty shallow, but there's just a huge list of exceptions. It would be like the equivalent of a gigantic switch statement or a gigantic if statement. The other problem is that we don't actually know the rules. So even if we were to sit down and write this enormous program to recognize the puppy, we don't know what the rules are. We'd have to ask like a puppy expert or something about how, waggly their tails are and how floppy their ears should be, right? We don't know the rules in advance. And the rules are too complex. They have too many exceptions and too many special cases. So writing the puppy detector is actually very difficult. So maybe instead of defining the input to output relationship by hand, we can define a program that acquires this relationship from data. See, with the puppy, it's a lot easier to give examples of what you want than to specify what you want in terms of rules. So if I want to add two numbers, it's very easy for me to code up, x plus y equals z. So it would be silly for me to instead give a bunch of examples, 2 plus 2 is 4, 2 plus 3 is 5, etc., etc., etc. That would be not a very easy way to do it. But with a puppy, it's the other way around. It's probably actually quicker for me to go out and photograph a bunch of puppies than it is to try to code up this puppy detector. So the key idea is that if the rules that describe how inputs map to outputs are complex and full of special cases and exceptions, then it's easier to provide data or examples than to implement those rules by hand. And I know that a lot of what I'm saying here is stuff that you guys probably already know because, kind of pretty clear from the example what I'm going for. I do think it's important to consider these basics, that this is really about situations where the rules that govern the transformation from input to output are complex and full of special cases and exceptions. And that's why we want to use machine learning. So machine learning is not, it's not some kind of magic thing. It's not the right solution to every problem. It's the right solution to problems where the relationship between the inputs and outputs is complex and full of special cases, so that it is easier for us to provide examples than it is to implement those rules by hand. Now, a question you could ask here is, well, does this also apply in some way to human or animal learning, right? Some things that you learn to do, you can follow some instructions. The instructions might be, if you're in this situation, then do that. You might have a checklist, right? If you're a pilot, if you fly an airliner, you get checklists, you get rules, you get instructions. But for other things, you much prefer to learn from examples. If you have to deal with complex and unpredictable situations. If you are a hostage negotiator, there are some rules. There's also a lot of practice. You might role play some example scenarios, right? You want to go through examples, go through possible situations, and then try to distill out those rules in a more intuitive way. So maybe some of these ideas apply to human and animal learning as well. Okay, so what is it that we're actually learning, or rather, what are our machines going to be learning? Well, okay, the puppy is pretty complicated, so it makes for a nice example, it's really cute, but we should work with something a little more manageable at first. So let's start with this problem. You have points in 2 dimensions, and you want to figure out if they're x's or o's, right? So in this case, the function that you're learning to map from points in 2D to a label of x or o could just be a line. So what are you learning? You're learning a line. But what is this computer program? Well, the computer program might look something like this. If x is below the line, then circle, else x. Right? So that's a computer program. And this function below line could be implemented like this. Take the first dimension multiplied by theta 1, take the second dimension multiplied by theta 2, add theta 3, and if that's less than or equal to 0, then report true, else report false. Right? So this is a computer program. But this computer program has some parameters. So with the code that I have here on the slide, this is not enough to fully specify this program, because I haven't told you what theta 1, theta 2, and theta 3 are. So you can think of machine learning as basically a computer program with some free parameters. In this case, the parameters are theta 1, theta 2, and theta 3. And this equation describes a line. So learning means figuring out what to set those theta 1, theta 2, and theta 3 to in order for the program to give you the right answer. So what we're learning is theta 1, theta 2, theta 3, or you can also call it a vector theta, which has 3 elements. And when you call it a vector, then you can also express this equation for a line as x transpose theta less than or equal to 0. Here you just assume that you append 1 in the third position. So the x vector is x1, x2, and then 1. So our parameterized program, it's going to be trained, and by trained I mean theta will be selected, so that this thing gives the right answer. And that is the process of learning. All right, so in general, we have some parameterized function, and we can call this function f. And it's really a function of two arguments. It takes in x, which is our input, and it takes in theta, which are our parameters. And it produces the answer y. And then the parameters theta, these are the things that are learned. Y is the output. If it's a classification problem, then we call it a label, and x is an input. We'll often see these types of functions written with the parameters as a subscript. So when I write f subscript theta of x equals y, I'm just using that to make it a little more clear that theta is a parameter of f. But really it's just another argument to f. And crucially, f theta of x can be almost any expression of x and theta. So here we have a very simple f. It's just an if statement with a line in it. But you could have f be something much more complicated. You could have it be a big complicated program with lots of parameters, or you could have it be a very simple program with lots of parameters. You could have a giant matrix represented by theta. Right, so there are many choices you could make. So which choice should we make? What parameterization do we use? What do we use if we want to classify the puppy? Well, here's the trouble. Puppies look pretty different. And yeah, I admit, when I was making this slide, I was just searching for pictures of cute puppies. That is, in fact, what I was doing. They all look different. And even the parts of puppies look different. So you could say, well, maybe puppies have 2 ears and 2 eyes. But their ears always look different, and their eyes look different. Is that a puppy? It also has 2 ears and 2 eyes. So there's a lot of ambiguity. There's a lot of complexity. And when we look at these pictures, we see parts and objects, we see colors. When the computer looks at the picture, it just sees a big array of numbers. Those numbers don't have any meaning by themselves. So thinking about this the same way that we think about separating out the x's and the o's, it might not get us very far. With the x's and o's, we could just draw a simple line through the xy plane and separate the two classes. But I don't think that'll separate the puppies from the cat here. So we're going to need something more powerful. We're going to need a different parameterized function. So classically, the way that people have thought about this, and I'll somewhat pejoratively call it shallow learning. I'm not trying to insult anyone. I just want to draw this as a contrast against deep learning, which is what we'll cover. So if it's not deep, it must be shallow. But don't take this too literally. Maybe it's more accurate to call this feature-based learning. Classically, the way people have thought about this is the following. We're going to represent our f theta as a fixed function, meaning a function that is not learned, that extracts some features from x. And then on top of those features, we'll perform some simple operation with learned parameters. For example, the linear classifier from before, that x transpose theta, one thing about it that was really nice is that it was very easy to think about, and it's actually very easy to learn the thetas. We'll actually describe a method for doing that a few lectures from now. So maybe we can keep that part, but instead of plugging in the entire image x into that linear equation, we would instead plug in some features of x. What might be the features? Well, maybe the features describe some way of extracting edges or corners, or maybe even something more complicated. Maybe we can even code up an entire ear detector or eye detector. Maybe we can have some features that are strongly indicative of the presence of eyes and ears that we designed by hand. One class of features, for example, that was often used in computer vision is something called the histogram of oriented gradients. The idea in a histogram of oriented gradients is the following. Extracting edges in an image is pretty easy. There are very good algorithms for edge detection. So what you can do is you can take a little patch of the image, find all the edges, and then construct a histogram describing the orientation of those edges. So if you see lots of horizontal edges, then the histogram has really big values for horizontal lines. If you see lots of vertical edges, then it has a big value for vertical lines. If you see lots of diagonal edges, you get the idea. And you do this in little patches of the image. And then you construct essentially kind of like a low-resolution image where each box contains a histogram of these gradients instead of the pixel values. And that's good because oftentimes a lot of objects are better determined by their shape than anything else, and edges capture some notion of shape, so these are good features to use for downstream classification. This kind of feature extraction approach, we could think of it as a kind of a compromise between the handwritten rules and machine learning. We don't hand program the rules, but we do hand program the features. So maybe we don't know how exactly to detect whether there's a puppy in a picture, but we know something about which parts matter, and maybe we can manually code up some rules for detecting those parts. And then learning on top of the features can be really simple, just like the 2D example from before. The trouble with this approach is that coming up with good features was very hard. In some cases, like computer vision, where people spend years and years studying how to construct good features, there were some good options available. Speech recognition, there's a lot of work on acoustics and speech formation, so people could design pretty good features. But in other domains, it was much harder to design good features. Domains where the data type is very peculiar, domains where we need to do something strange, like translating a low-resource language, for instance. So what does it look like to go from shallow learning to deep learning? Well, in shallow learning, we start with our input, and we have some features that we've coded up by hand, and then we have some learned parameters on top of those features. So all the parameters live up here at the very end. If the challenge is in programming in the features, well, what if we put some learned parameters in there too? What if phi of x is not just a function of coded up? What if phi of x itself has some free parameters? So then instead of manually programmed features, we have learned features. And the thing is, once we can learn the features automatically, we can put in many layers of features. And that's why it's called deep learning, because deep learning has many layers. So we would have our picture of a puppy. We would have our first layer of learned features, which would turn that picture of a puppy into some learned representation. Then we would have another transformation that turns it into a higher level representation, and so on and so on. And each arrow here, each yellow arrow in this picture, represents a simple parameterized transformation, a simple function of the preceding layer. But because we're composing many of these simple functions, the resulting function overall can be quite complex. And it can learn representations at every layer. Remember, those representations we talked about in the beginning, the representations of thoughts, of ideas, of abstract concepts. Here are some pictures of actual representations learned by a deep network. This is from a classic paper by Coates, Lee, Arena, and Ng. And here you could see the lowest level features look a little bit like edges. These are sometimes referred to as Gabor filters. It's actually widely known that the area of the primate brain, and also in general mammalian brains, that processes early visual signals also contains features very much like these oriented edges. It's not necessarily because the brain works the same way as a deep net, but it's because these features are just so useful for recognizing things in images. Then the mid-layer features, this is for a face detection system, look like parts of faces. You can see some eyes and some ears. These are not puppy eyes or puppy ears, these are human eyes and human ears. I unfortunately couldn't find features for a puppy detector. And then the highest level features look like objects and parts, so you can see foreheads and chins and things like that. There's also apparently some motorcycles and cars. I guess this also had cars and motorcycles, I don't know, or maybe people had cars and motorcycles on their faces, whatever. But anyway, clearly seems like there's some high-level object-like things going on in there. So higher level representations are going to be more abstract than the original pixels. They're going to be more invariant to nuisances. What does that mean? Well, the puppy at the bottom is still a puppy if it's facing in a different direction, or if it's illuminated differently, or if it's on a different color background. So those variables, we call them nuisance variables because they just get in the way of producing the right answer. So we'd like to ignore them. We'd like to get representations that are invariant to the color of the background or the direction of the lighting, so that we can focus on the stuff that matters, which is the puppy. And of course, these higher level representations make it easier to predict the label. So just like with the picture of the puppies before, the low-level pixels for these puppies all look very different. But the high-level representations, the presence of a nose or an ear or an eye, is more indicative of the presence of a puppy and more reliable. So we'd like to get those higher-level representations, and that's what deep learning is going to help us get. Okay, so what is deep learning? Well, it's machine learning with multiple layers of learned representations. So we want representations and we want to get them automatically from our data. Just like in the example with multilingual translation from before. The function that represents the transformation from the input to the internal representation to the output is usually a deep neural network. This statement is actually a little bit circular because almost all multi-layer parametric functions with learned parameters can be called neural networks. So more on this later, but don't let the term neural network confuse you too much. You might say, well, what is a neural network? Does it have something to do with neurons? Does it have something to do with networks? I'll tell you right now, pretty much any parametric function with multiple layers of representations could be called a neural network in one way or another. The parameters for every layer are usually, but not always, trained with respect to the overall task objective. So the representations of the puppy, the low-level, the mid-level, and the high-level representations are not just optimized any old way, they're optimized to get the network to be as accurate as possible at detecting the puppy. This is not always the case. We will talk about methods that separately learn representations and then learn to predict the quantity of interest, but oftentimes deep learning works really well when all of the representations are learned together so as to get the right answer. And this is sometimes referred to as end-to-end learning. It's called end-to-end learning because every part of the model is trained so that at the end it produces the right answer. Now, this might seem like an obvious thing to do, but of course, if you think back to the feature engineering approach from before, when we design the features by hand, we're not necessarily optimizing those features to give the right answer. We're rather using our bottom-up intuition about which features are important.